Namaskar. So, in last session we discussed about the magnetically coupled circuits. So, we will continue our discussion today and we will talk about energy stored in magnetically coupled circuits, and then also we will discuss about the ideal transformer. So, let us start the discussion of today's session. The energy stored in inductor, as we know, can be given by W is equal to half Li square. Now, to determine the energy stored in magnetically coupled coil, let us consider the following circuit. Here I1 and I2 are the currents on left and right coils. V1 is the voltage across first coil and V2 is voltage across second coil. They have inductances as L1 and L2, and M is the mutual inductance. Now, let us assume that first the current I1 and I2 are initially 0, that means that total energy stored in the circuit is equal to 0. Now, I1 is now allowed to increase from 0 to capital I1, that is one arbitrary value we are considering, while maintaining current I2 is equal to 0. In that case, the power in coil 1 can be given by P1 at any time t is equal to V1 I1. So, we can say as I1, V1 can be replaced by L1 dI1 by dt, and then the energy stored in the circuit can be given by, say, it is W1. So, you integrate the instantaneous power from 0 to capital I1 and solve it. So, when we integrate the above equation with respect to t, we get half L1 I1 square. Now, if current I2 is allowed to increase from 0 to, say, capital I2, that is again an arbitrary value we are considering, while maintaining the current same in the first coil. So, in that case the induced mutual voltage in first coil will be M12 dI2 by dt, while in coil 2 it will be 0 because there is no change in I1. So, dI1 by dt will be 0 when we are talking about the mutual induced voltage in coil 2. So, for coil 2 we will have the mutual voltage mutual induced voltage as M12 dI2 by dt. Therefore, the power in coils due to increase in current I2 can be given by, say, it is P2. So, it will have now two components, one is because of mutual voltage and second is because of the self inductance. So, this will become I1 M12 dI2 by dt and V2 I2. V2 can be given as L2 dI2 by dt because of the inductance, self inductance of the second coil. So, we can write I1 M12 dI2 by dt plus I2 L2 dI2 by dt. So, energy stored in the circuit because of change in current in the second coil from 0 to I2 will be, you will integrate the instantaneous power from 0 to I2. So, when you integrate you get the value as M12 I1 I2 plus half L2 I2 square. Now, in that case the total energy stored in the circuit will be considered when both I1 I2 have reached their constant value. So, total energy stored in the circuit will be now W1 plus W2. So, this will become half L1 I1 square, that is W1 plus M12 I1 I2 plus half L2 I2 square. Now, if we reverse the order by which the current reach their final values, that means first we will increase I2 from 0 to capital I2 and then we increase I1 from 0 to capital I1. In that case the total energy stored in the circuit can be given as half L1 I1 square plus half L2 I2 square plus M21 I1 I2. So, in this case the mutual inductance is M21 because the current which is increasing in the circuit first is I2. So, mutual inductance will be because of I1. So, you get the mutual inductance in the second coil as M21 I1 I2. Now, since the total energy stored should be same regardless of how we reach the final conditions, in that case if you compare these two equations, you can simply say that M12 is equal to M21. So, mutual inductance is this mutual voltage induced because of either first current is increasing or first current I2 is increasing or first current I1 is increasing will remain same. So, you can simply say M is equal to M12 or equal to M21. So, M12 or M21 in these two equations can be simply replaced by M. So, total energy stored in the circuit we can write as half L1 I1 square plus M I1 I2 plus half L2 I2 square. Now, this equation we derived by assuming that the currents in both coils are entering the dotted terminal, that means the mutual voltage which induced is in either of the coil will be positive. So, in case if one current enters the dotted terminal while the other leaves the other dotted terminal, the mutual voltage now will become negative. In that case, the mutual energy will also be negative. So, the total energy stored in the circuit will now become half L1 I1 square minus M I1 I2 plus half L2 I2 square. Now, we have considered I1 I2 as some arbitrary values. So, we can replace with any other value, like we replace with generic I1 I2 equations the symbols. So, what we can write, the instantaneous energy which will be stored in the circuit can be given by some general expression, and the general expression is W equal to half I1 square into L1 plus minus M I1 I2 plus half L2 I2 square. So, this plus minus will be depending upon how current is entering and leaving the dots. Now, the positive sign we will select when mutual term in both the positive sign we will select for the mutual term if both currents enter or leave the dotted terminals, otherwise we will consider as negative. Now, let us try to stabilize the upper limit for the mutual inductance. As we know, the energy stored in the circuit cannot be negative because we are talking about the circuit which is passive in nature. So, what we can conveniently say that half L1 I1 square minus M I1 I2 plus half L2 I2 square should always be greater than 0. Now, we have two square terms in the expression. So, what we will do, we will first create the complete square. So, to do that, what we will do, we will add and subtract I1 I2 under root of L1 I2 basically in the expression. So, when you add as well as subtract I1 I2 root L1 L2, you can simplify the above expression as half I1 into under root L1 minus I2 into under root L2 whole square plus I1 I2 root of L1 L2 minus M greater or equal to 0. Now, since this is the square term, this can never be negative, at most it can be 0. So, we can have the updated constraint or the criteria that the root of L1 L2 minus M should be greater or equal to 0. So, we get updated criteria now. So, if you simplify, you get M should always be less than or equal to L1 L2 whole under root. So, that means the mutual inductance cannot be greater than the geometric mean of the self inductances of the coil. Now, this condition we can convert it into equality constraint. So, when you convert it into equality, let us multiply with some constant k. So, we can write m is nothing but k into root of L1 L2. This k is called as coefficient of coupling. So, coefficient of coupling is the measure of magnetic coupling between two coils. So, the value of k will be ranging between 0 to 1. So, if k is 1, we will say that the circuit is perfectly coupled. If k is less than 0.5, we say that circuit is loosely coupled, and if k is greater than 0.5, we say it is strongly coupled. So, now let us take one example to understand what we discussed related to energy stored in the coupled circuit. We need to find out the energy stored in the coupled inductors at time t is equal to 1 second, where voltage V is given as 60 cos 4t plus 30 volt. Now, if you see this particular circuit, the L1 L2 are given as H4 and H4 5 and 4 Henry. So, K will become M is 2.5. So, K will become 0.56. So, since K is 0.56, we will say that the circuit is tightly coupled. If K is less than 0.5, we will say that it is loosely coupled, and in case K is equal to 1, we will say circuit is perfectly coupled. Now, the next task is that to find the energy stored, we have to calculate the value of current. So, for that what we need to do? We need to first obtain the frequency domain equivalent of the circuit. So, when you convert it into frequency domain equivalent, your voltage will become 60 angle 30 degree, and the omega value is 4 radian per second. The 4 Henry inductor will be now J20 as a reactance, 2.5 Henry mutual inductance will become J10, 4 Henry inductor will become J16 as its reactance, and then the capacitor will have the capacitive reactance of minus J4. So, if you put all those values in the circuit, you will get the circuit in frequency domain. Let us assume that the current I1 is flowing in the left part of the circuit and I2 is flowing in the right part of the circuit. So, if you see these two currents, both are going inside the dot, that means the mutual voltage will be positive. So, for mesh 1 what we can write? For mesh 1 we can say the value of impedance, that is 10 plus J20 multiplied by I1 plus mutual voltage, that is J10 I2 equal to the applied voltage 60 angle 30. Now, for mesh 2 what we can write? We can write minus J4 plus J16 into I2 plus J10 I1 because of mutual voltage equal to 0. So, from this we get I1 is equal to 1.2 I2. Now, this value if you put here, the updated equation will be minus 12 plus minus J14 into I2 is equal to 60 angle 30. So, when you simplify, you get the value of I2 as 3.254 angle 160.6 degree. Now, you can get the value of I1 as 3.905 angle minus 19.4 degree ampere. Next task is that we will convert now the values of current we got into time domain. So, I1 will become 3.905 cos 4t and minus 19.4, I2 will become 2.354 cos 4t plus 160.6 degree. Now, we need to find the value of energy at time t is equal to 1 second. So, in the voltage, if you see the voltage value, it is 60 cos 4t plus 30. So, that means that the value 4t will be the omega t value in the expression, So, in that you just put the value of t as 1. So, you get the angle as 4 radian. This 4 radian we need to convert it into degree. So, if you convert 4 radian into degree, you have to just multiply by 180 degree divided by pi. So, when you simplify, you get angle, that is instantaneous angle at t is equal to 1 as 229.2 degree. So, you put this value here. So, I1 at time t is equal to 1 second will become, now if you simplify, this will become minus 3.389 ampere. Similarly, I2 will be 2.284 ampere. So, the total energy stored in the coupled inductors can be given as W equal to half L1 I1 square plus M I1 I2 plus half L2 I2 square. You put the values of I1 and I2 and L1 L2 and M, and when you simplify, you get the value of total energy stored as 20.73 joule. Now, let us start the discussion about the another topic called ideal transformer. Now, what is ideal transformer? The ideal transformer is the one which has perfect coupling. So, it means that if you have the magnetically coupled circuit and you have the coupling coefficient equal to 1, that means the circuit which has perfect coupling will be the ideal transformer. So, it consists of 2 or more coils with a large number of turns wound on a common core of high permeability. Since we have high permeability in the transformer core, the flux which will be generated links to all turns of both of the coils, thereby resulting in perfect coupling. So, what we can say that ideal transformer is the limiting case of two coupled inductors where the inductances approach infinity and the coupling is perfect. So, to understand this more clearly, let us consider one circuit of the ideal transformer. So, in this case, if you see V1 is applied on the left side of the coil, V2 is at the right side of the coil, M is the mutual inductance, L1 and L2 are the self inductances of both coils. Now, I1 and I2 both are entering the dot, means the mutual voltage would be positive. So, what we will do, we will write the equations for V1 and V2 in frequency domain. So, if you write equations in frequency domain, you can write V1 is equal to j omega L1 I1 plus j omega M into I2 because of the mutual inductance. So, from this you can simply say I1 is equal to V1 minus j omega M I2 whole divided by j omega L1. Now, for the second coil V2, you can write j omega M I1 plus j omega L2 I2. So, what you will do now, you will put the value of I1 in this equation, and when you simplify, you will get V2 is nothing but equal to j omega L2 I2 plus M V1 by L1 minus j omega M square I2 divided by L1. Now, you know that M which we have just now derived is equal to root of L1 L2 in case of perfect coupling. So, when you consider k is equal to 1, means perfectly coupled coils, M will be equal to root of L1 L2. Now, this value we will put in the previous equation, and when we simplify, we get V2 is nothing but j omega L2 I2 plus root of L1 L2 in place of M into V1 divided by L1 minus j omega L1 L2 I2 by L1. So, when you simplify, you get the value as V2 equal to root of L2 by L1 into V1. So, now if you just say root of L2 by L1 as n, we can simply write V2 is equal to n V1. Now, what is n? N is popularly known as the turns ratio of the transformer. So, if you see the expression, if L1, L2 or M tends to infinity in such a manner that n remains the same, the coupled coils will become the ideal transformer. So, to summarize, we can say the transformer is said to be ideal if it has the following properties. Coils will have very large inductances, means L1, L2 and M tends to infinity. Coupling coefficient is equal to unity, that is K is equal to 1, and primary and secondary coils are lossless, means the resistances of the primary and secondary coils are almost equal to 0 in case of ideal transformer. Now, an ideal transformer is a unity coupled lossless transformer in which primary and secondary coils have infinite self inductances. The circuit symbol of transformer we generally show like this, where we have the coil 1 and 2 and have the turns ratio N1 and turns, number of turns in primary coil as N1, number of turns in secondary coil as N2, and the double lines in between two coils shows that the core is present in the transformer. Now, primary winding is having N1 turns and secondary is having N2 turns. So, what we will do now? We will apply the sinusoidal voltage in the transformer circuit which we just saw, and the magnetic flux in that case generated will goes through the both of the windings. So, you can simply apply the Faraday's law to find out the voltages V1 and V2 when you apply voltage in the primary coil. So, what will happen? You can say V1, that is induced voltage, equal to N1 d phi by dt, because this flux phi is linking both of the windings. So, V1 will become now N1 into d phi by dt, and induced voltage in secondary coil V2 will be N2 into d phi by dt. Now, if you divide both of the equations, we get V2 by V1 is equal to N2 by N1. This will be equal to N, which we just derived, which was the turns ratio of or the transformation ratio of the transformer. So, if in case of instantaneous voltages, that is V1, V2, if we write phasor voltages, that is capital V1 and V2. So, we can simply say that V2 by V1 is equal to N2 by N1, which is nothing but the turns ratio of the transformer. Now, the if for the reason of power conservation, the energy supplied to the primary should be equal to energy absorbed by the secondary. So, when you follow the law of energy conservation, the value, that is V1 I1 should always be equal to V2 I2 in case of ideal transformer. So, what we can write now? So, if you write like V1 upon V2 will be nothing but I2 upon I1. So, if you write it in the phasor form, you can write V1 upon V2 is equal to I2 upon I1. V2 upon V1 we have just now found, that is equal to N2 by N1, which is nothing but equal to 1 by N. So, what we can write? We can write that I2 by I1 is nothing but equal to N1 by N2 or equal to 1 by N. So, when N is equal to 1, we say transformer is called as a isolation transformer. When N greater than 1, it means that we have the step up transformer, and when N is less than 1, it is called step down transformer. What is a step down transformer? A step down transformer is the one whose secondary voltage is less than the primary voltage, whereas in case of a step up transformer, the secondary voltage is greater than its primary voltage. So, now it is important to get the proper polarity of the voltages and directions of the currents for the transformer. So, if the polarity of V1 or V2 or the direction of I1 or I2 is changed, the value of n which we have just saw may need to be replaced by minus n. So, how to find out whether we should use plus n or minus n? We will simply use the following rules. What are the rules? If V1 and V2 are both positive or both negative at the dotted terminals, then we will use plus n in the transformer voltage equation, otherwise we will use minus n. If I1 and I2 both enter into or both leave the dotted terminals, we will use minus n in the transformer current equations, otherwise we will use plus n. So, if we follow these two rules, the possible combinations for voltage and current are 4. So, we can have 4 possible combinations of circuits for the ideal transformer. Let us see what are those 4 circuits. So, in first, if you see V1 and V2 both are positive at the dotted terminal. So, we can say V2 by V1 is equal to plus N2 by N1. Now, since current I1 is going inside and current I2 is going outside the dotted terminal, that is why I2 by I1 is also plus N1 by N2. Now, in this case the voltage terminals are positive at the dotted side of the terminal. So, we write V2 is equal to N2 by N1, V2 by V1 is equal to N2 by N1. But now, the direction of current is opposite, N1 and I1 and I2 both are going inside the dotted terminal. So, I2 by I1 will now become minus of N1 by N2. Now, in the third case, the value of the voltages in left side, the dotted terminal has negative polarity of the voltage, and at the right side you have positive polarity of the voltage. So, we will write V2 by V1 is equal to minus of N2 by N1. Now, in case of current, in both of the coils, if you see in this case current I1 is going outside the dotted terminal and I2 is going inside the dotted terminal. So, I2 by I1 will become plus of N1 by N2. Now, in fourth case, your voltages are having the same polarity as we saw in this case, where V1 is positive at the dotted terminal, while V2 is negative at the dotted terminal. So, we can write V2 by V1 is equal to minus of N2 by N1, while in case of current, if you see current is going, I1 is going inside the dotted terminal, at the same time I2 is also going inside the dotted terminal, because if you trace the path of the current, I2 will go inside the dotted terminal from here and come out from the upper side. So, in that case what will happen, you will write I2 by I1 equal to minus N2. So, with this we can close our today's discussion, in which we discussed about the energy stored in magnetically coupled circuits, and also discuss about the ideal transformer and their various connections and the polarity. We will continue our discussion related to the ideal transformer also. Thank you.